Hi, this is Mark Weitzman. Welcome to my channel, Theoretical Physics with Mark Weitzman. Today I want to do another simple problem in electrodynamics, classical electrodynamics, and this one is from Modern Electrodynamics by Zangwill, which is an excellent graduate level textbook. It's very thorough. I think it's considerably easier than Jackson, but it has most of what you need. And so this is a early problem in the book, problem 313, and I'll just read it for you. A uniformly charged cube. The figure below shows a cube filled uniformly with charge. Determine the ratio phi0 over phi1 of the potential at the center of the cube to the potential at the corner of the cube. Hint, think of the cube as formed from the superposition of 8 smaller cubes. So they've already told you how to do the problem. And this problem, in the answer solution, which I looked at after I solved it by Zangwill, he mentions that it's a problem that's also in Purcell's book, second edition. So I think he copied the problem. Anyway, just from reading the problem, there's a problem with the problem. And the difficulty is that it wants to know the ratio of phi 0 over phi 1. Now, as you remember from electromagnetism, the potential is not determined. It's you can always, even in static electromagnetism, you can always add a constant to it. So how do we know? We need to define in order to make this problem well defined, we need to at least say or define what the zero of the potential is. Now, to do this, we'll make our standard choice. And we'll have the potential phi at infinity equals 0. Now the problem is well defined. And before I solve this problem, I just want to review, in case you're trying to remember, what would the answer be if instead of it was a uniformly charged cube, we had a uniformly charged sphere. So if we have a uniformly charged sphere, say the charge density is rho, the radius of the sphere is a, what would be the ratio of phi on the surface A? Okay, we want and phi at the origin divided by phi A. So to do that, we'll just do the calculation that's done in every freshman physics class. We'll start with what we'll do is we'll integrate from infinity. Consider this point infinity. And we'll just integrate. We'll start by integrating from 0 to the point A, and then we'll continue on to the origin. So let's just use Gauss's law. We have the electric field, and I'm using the same units that Zangwill uses. My personally despised MKS units, but that's what he uses. That's what I'm going to do. 4 pi r squared is the surface, and this is equal to the charge 4/3 rho a cubed divided by epsilon 0. So this implies that E is equal to rho a cubed 3 epsilon 0 r squared. So phi at A is the integral minus the integral from infinity to a of the electric field dr rho a cubed 3 epsilon 0 r squared. And this is just equal to rho a cubed over 3 epsilon 0 r. Because when we take the derivative, we get minus 1 over r squared, so that helps us account for the minus sign in front. Over there, we go from infinity to a, and we get this is rho a squared over 3 epsilon 0. And if you want to rewrite that in terms of the charge, you would get q over 4 pi a epsilon 0. Remember, q equal to 4/3 pi rho a cubed. Okay. And then if we want to get the potential at 0, it's going to be the potential at a, and now we're going to integrate minus the integral from a to 0 to the origin, dr. And now I have, I didn't get the electric field inside, so let's do the electric field inside. It's E times 4 pi r squared now, and this is equal to 4/3 pi rho r cubed, the charge inside the sphere, inside the radius at r. So if we were integrating this thing over here, this would be a radius of r. Divided by epsilon 0. And that implies that E is equal to rho r over 3 epsilon 0. So I put that here. I have rho r over 3 epsilon 0. And this is equal to phi at a, we've already evaluated, rho a squared over 3 epsilon 0. And then I have minus rho r squared over 6 epsilon 0 evaluated from 0 to a. At 0 we get 0, so we just gonna we get rho a squared over 3 epsilon 0 plus rho a squared over 6 epsilon 0. And this is just rho a squared over 2 epsilon 0. So phi of a, we got this. Now we're getting this. And we want the ratio. The ratio of a phi of 0 over phi of a is equal to rho a squared 2 epsilon 0 divided by rho a squared 3 epsilon 0. This is equal to 3/2. Okay, so that's the answer for a sphere. Now we can't do this with a cube. The integrations just become too difficult. I'm not saying they're impossible. Certainly they could be done numerically. But it's just very hard to do. So let's think a little bit about the cube. We're going to, we have a cube. I'm not very good at drawing these things. So this is our cube. We want to compare, let's say, over here to the center. Now, we can divide the cube 8 parts is recommended. So this is a side A. So this 8 parts would just be 8 cubes of side A over 2. Now, if we were to look at one cube, one of the smaller cubes, let's say this would be the center of the big cube. So, regardless of what the potential here is on the edge, let's do it like this. When we integrate, we would integrate from here, we would divide by R, and we would add up, we would get the potential from the cube. At the corner of the small cubes, the potential is all the same. So this is like, let's call this, whatever it is, we don't know what it is. This is the potential at the corner of a cube of side A over 2, but it's also going to be equal to the potential of a cube of side A when we have the bigger ones over here. It's not going to, I'm just looking at the potential of this cube by itself. Let's just leave that off. So what we have is that phi at 0, the phi at the center of the cube, our master equation is that phi at 0 is going to be 8 times, because there's 8 cubes, 8 times the potential of phi at A over 2. In other words, looking at this cube alone, the potential here and the potential here are the same. We just want to add up all the potentials at the center, so it's as if we had taken the potential of a cube on the corner at phi of A over 2, and we did that 8 times. So let's, how would we calculate that? Well, phi so phi at A over 2 would just be, we would integrate from minus A over 2 to A over 2, the integral from minus A over 2 to A over 2, the integral from minus A over 2 to A over 2, dx, dy, dz, rho over the square root of x squared plus y squared plus z squared. In other words, we simply have a small cube, side is A over 2, and I have the charge, and I'm going to use the usual formula for the charge density divided by the distance. So this is, I'm just going to integrate, from let me see if I got that right. Phi of A over 2. Yeah, so imagine we have a coordinate system which goes from minus to plus. And we're just going to change the variables. I just want to check something here. So I think I'm doing this a little bit wrong. I really should be integrating just from 0. Sorry. Doesn't affect the answer in any way, but and so I'm just integrating. Let's say I want to know the potential at this corner. I just integrate from 0 to a over 2 in all three dimensions. I take a point here, which has coordinates x, comma y, comma z, and I just take the charge density, which is uniform, divided by the distance, and that will give me the potential there, which is equal to the potential here. The potential at the cube is all the same. It's the same calculation. So that's how we get that. Now, to do this, I simply change variables first. So I'll go x prime is equal to 2x, y prime equal 2y, z prime equal 2z. Now I'll get dx, dy, dz is equal to 1/8 dx prime, dy prime, dz prime. And now my integral will just be phi 1 a over 2. I'm sorry, I didn't define the 1. 1 means corner. I do that. So phi 1 a over 2 is equal to the integral. Just make the usual substitutions. The integral from 0 to a, the integral from 0 to a, the integral from 0 to a, dx prime, dy prime, dz prime. I have a 1/8, and I have a row, square root, and I get x prime squared over 4 plus y prime squared over 4 plus z prime squared over 4. Okay, so this is going to end up, the 4's, the square root is going to be 1/2 in the lower denominator, so that's going to make the whole thing 1/4. So I get 1/4 the integral from 0 to a, the integral from 0 to a, the integral from 0 to a, dx prime, dy prime, dz prime over the square root of x prime squared plus y prime squared plus z prime squared. And this is just equal to 1/4 of the potential at a corner of a cube with side A. So that's just the scaling, and you could have easily figured this out without doing this computation. So I have phi, let me see the notation that I used. Phi at 0, let's just say I have phi of 0, which is the center, of a cube of size A is equal to 8 times the potential at the corner of A over 2. And the potential at the corner of A over 2 is 1/4 of the potential at the corner of a sphere of size A. So this is equal to 2 times phi 1 size A. So this leaves phi at the center psi A over phi at the corner size A equals 2. That's the answer to our problem. So it's a little bit higher than for a sphere. And so what we're doing is we're just adding up the potential from the 8 cubes. We could think of it as the potential at the right lower corner of, let's say, the top cube. The potential of the cube of each cube at the center. We have 8 cubes that meet at the center, and at each point the potential from that cube that gives us to the center is just the same as You know, this, they're all the same. So if I want to start with this, I could calculate it like I did here, but also it's the same as at the center. And so we get our result. So this is just a simple calculation showing how superposition can handle some simple problems. And I guess this is not surprising. Like I said, for a sphere, it's 3/2. But with the cube, there's a lot of points that are like, farther away on average. With the sphere, every point is a distance a away. But with the cube, there are points relative to this center. If the cube is size a, this is going to be a divided by, or let's see, if the whole thing is going to be times the square root of 2 divided by 2, so it's a over the square root of 2. So it's, that can't be right. Yeah, so a over the square root of 2. So this distance, if we consider the radius of the cube as a over the square root of 2, if we consider the radius of the cube as a over 2, then the distance to the corners is a little longer than for a sphere, like if we had that. So that's why it's not surprising that the potential at the origin is a little bit higher than for a sphere. Anyway, you can reason it out and probably convince yourself one way or another, but the best thing is to calculate it. And so I'll end this video here. I know it's a little confusing in some spots, but if you just think about it and think about the scaling argument, which works not just for a cube, but also for a sphere and for everything, you're going to get the scaling argument as 1/4. So thank you for watching, and I'll be back next time with another EM video soon.